All right, this is vectors 2, day number 5. Day number 5. Excuse me, vectors 2, day number 4. Okay, we're going to be using normal form to find the distance from a point to a plane. So let's get started. All right, you guys, I want to narrow this down. This is a lot of information here. If I could give you the most important items on this slide, it'd be right here. Okay, and I'm not necessarily worried about how we got there. Okay, I'm just giving you the hamburger. But n hat is the unit vector in the direction of the normal. R is just the plane, okay, the plane R, which would be, ax plus b, y plus c times d plus some constant, right? And then this lowercase d is going to be a distance, okay? And this uppercase d is this d right here, right? This value, whatever this value is, when I have it over on this side of the plane equation, that is capital D. Okay, so let's move to the next slide. I'm not going through much of this slide just due to the fact that I don't have time for it. If you're curious, you can inquire in class. We can talk about it on this side. Okay, so finding the distance from a plane to the origin. Let's take this point here. Let's call it the origin. All right, 0, 0, 0. The distance, the shortest distance to that plane will be lowercase d. And I should have done that in red to model that from over here, right? That's this d here. Okay, so what you'll notice in both of these equations, right, that they nicely and conveniently prove for us is that r is a component of both of those, right? This is just the vector, or the plane, r, which would be whatever that plane is, right? So here I have a plane. We'll get to that in a minute. Okay, so if I were to solve for r in the first equation, r equals lowercase d over n hat, which is the unit vector in the direction of the normal. In the second equation, if I solve for r, I get capital D over the vector n. Now, if that's true, then what I know is that d over n hat is equal to capital D over our normal. Okay, and I'm just going to do some algebra here, cross multiply. D times our normal vector would equal capital D times the unit vector in the direction of our normal. Now, I want to just take off to the side here for a moment. The unit vector in the direction of our normal is 1 over the magnitude of our normal times our normal. Okay, that's just the definition of the unit vector. Therefore, I'm going to do a direct substitution of that. Okay, so d times the normal equals capital D times the unit vector. I'm going to substitute in there for that unit vector the following. And put the magnitude of the normal on the bottom and the normal on the top. So I'm going to divide both sides by the normal. Okay, and what you see is something actually really cool, is is what we get is the normals cancel, and I just get capital D over the magnitude of the normal. And that's going to tell me the distance, right? That's going to tell me the distance that this plane is from the origin. Okay, so I got 3, 4, negative 2, 3x plus 4y minus 2z equals, is it 11? Yeah, 11. So all I need to know to find the distance is I need to know capital D. I have capital D right here. And I need to know the magnitude of the normal. Well, the normal of this plane is 3, 4, negative 2. So the magnitude of the normal would equal the square root of 9 plus 16 plus 4. Looks like I'll get the square root of 29. So the distance from the origin to this plane is 11 over the square root of 29 units, whatever that comes out to be. Okay, let's keep moving on to another example. All right, so a distance from a point, let's put other than the origin, a point not the origin, to a plane. So I want you to imagine for a moment, I'm just going to sketch something here. Here's a plane. Here's the origin. Let's put the origin down here. 0, 0, 0. Here's the normal. Solid line and then dotted line. All right, so there's our normal to the origin. Right? Let's say we want to know the distance from some other point. Right? Let's just call it P. Right? Some point P. I don't know what that point would be, but I can just make it up, right? Okay, so how would I find the distance from that point to this plane? So draw another normal. Well, what I can do is I can find this distance to the origin. Right? I can also find this distance from the origin. Okay. Well, how would I do that? Well, what I would do if I were you is I'd create a second plane, which we can do. I'll show you in a minute how to do that. And I can draw a second plane that goes through that point. Okay, so really what we have is, this point, this origin point is beneath, right? Is beneath this plane. Right, so basically we've got. Let me see if I can highlight to make this make more sense. That makes more sense. Okay, so those points are beneath this plane. Right? Point P is on the plane. The origin and this other point, we could, whatever we want to call it, we could call it Q. Right below the plane. What we can do here is we can take distance 1 and subtract distance 2, and then take the absolute value of that, and that would be the distance from the plane, the original plane, this one's called plane P, to, that's a terrible idea, plane, let's call it plane pi. How about that? Call it from plane pi in honor of, well, math. What else? Plane pi to point P. So look at it from a horizontal viewpoint, right? So there is the origin, right? And then I've got this distance here. And then I've got this other point, I'm calling it P. And I can find this distance here, which we call D2. And so when I subtract, I get this D1 minus D2. And the reason we do the absolute value is because potentially the value you get when you take the first distance minus the second could be negative. All right, so I had created the second plane right here. And so now you can see that that blue segment right here is going to be the distance between the point and the plane. So let's go through one. So let's find the distance from the plane to the origin, which we just figured out an equation for. Come on now. Distance equals capital D over the magnitude of the normal. Okay, so capital D in this case looks like it's 4. Magnitude of the normal. Oh, what is the normal? The normal is 2, 1, negative 1. Where did I get that? Oh, I got it right here. 2, 1, negative 1. Okay. And then I take the magnitude of that, and it would be square root of 6. So the distance from the plane to the origin would be 4 over root 6. Find a plane parallel through the point. Find the distance from the plane to the origin. So here's this point 1, 2, 3. Right? I want to sketch a plane there, right, where this is normal also goes through, is normal to that plane, right, parallel. And I'm just going to make, an equation of a plane using what I know. So I'm going to take, if you recall, AP dot with the normal, and that should equal 0. So AP would be x, y, z minus 1, 2, 3, dotted with the normal, which is 2, 1, negative 1, should equal 0. So let's do that. That means I get 2x plus y minus z. I'm going to go back and do the constants. Minus 2 plus 3 equals 0. So that gives me 2x plus y minus z minus 1 equals 0, so equals 1. Okay, so now all I have to do to find the distance from this plane to the origin is to do the same thing I did up here. So the distance will equal capital D. Capital D is 1 over the magnitude, which will not change, over the 6. So those two distances are different. So then the distance from point 1, 2, 3 to the original plane is going to be distance 1 minus distance 2. And we'll take the magnitude of that. Well, that would, or not the magnitude, I'm sorry. The absolute value. This is not magnitude. Not magnitude. Lots of details here. So I'm going to take 4 over root 6 minus 1 over root 6. And it looks like the distance is going to be 3 over root 6. So the distance from point 1, 2, 3 to this plane is 3 over root 6. All right, if you want to try one on your own, go right ahead. Feel free to do so here. I'm just going to put the work down. You can feel free to continue to watch this video if you'd like. Otherwise, you can pause it and come back and check the answers. Okay, so to find the distance, I'm going to take big D or capital D, which is negative 13. Remember, you got to move it over here to find out what that is. Over the magnitude of the normal. The normal is negative 3, 2, 5. So it looks like the square root of 9, 4, 25, which would be 34, 38, square root of 38. Okay, the second would be to create a plane using this point and then do the same thing. So what I would do is I'd take x, y, z minus 7 minus 1 minus 1 dotted with the normal. We know our normal is going to be the same. I want to create a plane that's parallel, set it equal to 0. So we get negative 3x plus 2y plus 5z plus 21 minus 2 minus 5 equals 0. So that's negative 3x plus 2y plus 5z. What is that going to be? Plus 14. So scratch that. I'm going to have minus 14 over here. Okay, I think we're good. Let me check my numbers. Yep. Okay, so now to find the distance from that point to the plane, or to the origin, would be to take negative 14 over the square root of 38. So we've got distance 1, we've got distance 2. We're going to do simple subtraction, negative 13 over root 38 minus a negative 14 over root 38. Looks to be positive 1 over root 38. That will be the distance from 7, 1, 1 to the plane negative 3x plus 2y plus 5z plus 13 equals 0. Now that will be the minimum distance, the shortest distance from that point to that plane. Hopefully that makes sense. Go ahead and ask questions, and we'll see you soon.